So as we see that this is our question number 1, these are the states written here like this. These are the different variables that we have. These are the symbols that we will be dealing with, and this is what's on the tape, of course, and this is our accepting state. Now looking at this table, we can easily translate this table into something like this. For example, that the question was that stimulate the machine on the input, this is the input, and track the state head and tape. So what it does is that it scans right through the first block of ones, replaces the 0 with a 1, merging the blocks basically. Scanning to the end of the second block, deletes the very last one, and then returns to the start of the tape before halting. Meaning that the tape performs, this was the operation, it performs, for example, 1 1 1 1 1. It has 1 2 3 4 5 ones. Then we have 1 2 3 4 5 6 ones. Meaning that, imagine if we have 1 2 3 4 5 here. This is a 0. This becomes 6 now. Basically, x plus y in unary. So the only way to do it is just make this a 1, and then the separation is, so it's basically separated by a 0. If you remove the separation, then it's basically concatenated like this. Then we have 3 here. If I want to make 5, I just bring this closer, then we become 5. That's what's happening. And the way it's happening is that first it's in S0, it reads a 1, it stays there just like that according to a rule, moves right. So now S0 is reading a 1, and that's what we see. It reads a 1, it goes right, then it reads a 0. Now make it a 1. That's what the rule says, make the 0 1. The moment you see in S0 you see a 0, make it a 1. That's what it did. And also transit to S1. After transiting to S1, keep going right, stay in S1, keep going right. The moment you see the hash, like the and symbol, go one step back and go to S2. And now it's in this state, it's reading a 1. It's going back to S3. 3 4 5 6. So we 1 2 3 4 5. So 1 2 3 4 5. So it was 1 2 3 4 5, right? But if we somehow remove this 0 with 1, then it will be 1 2 3 4 5 6, right? But actually what I think is that it's putting it together. For example, if this 0 becomes 1, this is actually adding the both strings. But in the end we get 1 2 3 4 5, right? So blanking the last bit, basically the last one, if we make it a blank and then change the state, then we are basically getting rid of this 0 actually. And then we go all the way to the left, and then we finish basically. So describe what it really did. It computes unary addition. So just like I said, x plus y, by concatenating two separate blocks of ones and removing the ones to account for the 0 separator. We initially had 1 1 1 1 1. What's the addition of it? 1 2 3 4 5, right? So there was a 0 here. If I make this 0 a 1, this basically becomes 6, and we don't want 6, we want 5. So then we get rid of the last first we had here. Basically that's it. And this is addition then. This is what it does. So two-way Turing machines. Difference between an ordinary Turing machine and a one-way Turing machine. An ordinary Turing machine has tape that stretches infinitely on both left and right directions, and whereas one-way Turing machine has a hard left physical boundary that reads right, head cannot cross. So there is a limit on one side. An ordinary Turing machine is like endless road, while one way is like measuring tape that starts strictly at 0 but unrolls endlessly on the right. Now, How can the left end of the tape be marked? You can place a special marker symbol in the very first cell of the tape, so the machine explicitly knows it has reached the physical boundary, meaning if the head reads a special hash or a diamond symbol, the transition rule forces it to immediately move right to avoid crashing off the edge. So the edge is separated by some kind of marker that we know that this is the edge, and we know that we cannot go beside that. So there's always a special symbol that translation forces to immediately go right to avoid crashing off the edge. How can ordinary Turing machine be simulated by one-way infinite Turing machine? It folds the two-way infinite tape into parallel tracks on a single one-way tape, using track 1 for positive cell coordinates and track 2 for negative cell coordinates. For track 1 positive positions like 0, 1, 2, 3, and then we have -1, -2, -3, right? Now everything that is on the minus side here on infinite, we put it here by making space. We make some space here, extra blanks, and we move everything on the right, and we put all of these minus spaces here on the positive side. So we have the same exact spaces used in both situations, or cells used basically. Why do models have the same computational power? An algorithm written for two-way tape can be perfectly and mechanically stimulated on folded one tape without losing any data or capacity. So folded map one way contains exact same city, exam say information. Unfolded, everything that can be solved by a two tape can also be solved by a one way. So that's why if it can be solved, just like we mentioned, how can we do it? We can do it by doing this. We can make spaces, and because it's infinite on the right hand side or either one of the sides, it will never lack the space to convert it to a one-way Turing machine. And because both of them can solve the same amount of problems, they basically have the same computational power. Now we need to encode this using the urinary format. Now what happens is that we basically use these, and we look into because these are constants, we don't change them, these are constants, we only look for this, and we look in the symbols. For example, what does S1 translate to? What does 1 translate to? What does S1 translate to? What does this translate? What does this translate to in the code? And based on that, we just write it on the positions. And once we write it, then we find, okay, the coding is that 0, and then whatever it was, 1 for example, and then 0, and then whatever we had, and we just write it. That's really basic and simple. And we can actually see it as well in if there is any possible. But anyways, that's the concept. That's the same thing for encoding any other. We might be given this, and we might be given this, just like we see, and based on that we just encode it, which translate to 1 1 1 1, for example. There are rules defined for all of these. We look at the rules, and then we just put it in the values. And that's the same for the other one. Maybe I can also try to look at this way. Maybe I have it somewhere here. Yes. For example, we can see that this encoding, for example, what is a box? We can see it in here. It's the box is a 1 1 1, so we know the box is a 1 1 1. It should be a 1 1 1. So then see 1 1 1. There is S1 according to this. There is state. Then there is this. Then there is this. Then there is different. Then there is the direction. So we have a state. What S1 is a 1. We always know S1 is a 1 according to our table. Then we know a box is a 111. Then we know we just need to first fill all of this into this, and after we do this, we can easily take this from this, and that's the same thing for this too. Now, which properties must a Gödel numbering satisfy? It must be uniquely encoding, meaning injective. The rest of meaning that every single x goes to a unique y. Both are uniquely to each other. So two machines cannot have the same Gödel number. It's like a S number, SID. The set of valid encoding must be algorithmically decidable, and both the encoding C and decoding functions must be fully computable, meaning you can convert Gödel number into that numbering and then numbering back into the Gödel number. Like a retail barcode system, every product gets a barcode. The scanner knows if a barcode is fake, and the computer can translate the code back to the product name. So looking at the code, you can go back to the product, and the product you can go back to the code, and the scanner knows if it's fake or if it's not really accurate. Now, why must C be injective? It must be strictly injective so that every encoding number tracks back to exactly one unique machine. Injective meaning that it's unique. And why does it needs to be unique? It needs to be unique so that it tracks back to the same machine, avoiding any ambiguity. Because then if there's ambiguity, then we don't know if it's going to this and that at the same time. We don't know which one you're talking about if it's going to the same. So there needs to be always unique. If two entirely different software programs share the exact same ID number, the computer wouldn't know which one you actually want to run. Now, which must it be decidable whether a number is a valid encoding? Now, you must be able to algorithmically verify if a random string of numbers represent a valid, safely runnable program or just broken syntax errors. For example, the operating system needs to check if a file is actually exe program before it blindly tries to execute it. And that's true actually. You cannot run anything when it's not even runnable. So we must be able to verify if a random number of strings represent a valid, safely runnable program, or is it even something that's going to some rules, or is it just random numbers or broken syntaxes? Now, why must both C and C minus be computable? We need to mechanically translate the Turing machine into a number for storage and then mechanically translate that number back into the machine rules for execution. For example, a zip file is useless if you have the algorithm to compress it but lacks the algorithm to decompress it and read it later. So you can encode it but you cannot decode it. Then what would you use it? How would you use it? If you can encode something into encryption, you can make a password into it, but then you can never really convert it back. Then it's basically useless. Does a Gödel number have to be bijective? No. There are many random numerical strings that represent valid syntax and do not map to any real Turing machine. For example, the string 010110 might decode perfectly to a machine rule, but all of these zeros is just gibberish that doesn't decode anything. So there are things out there that don't decode to anything basically, but there are strings that you might decode perfectly to a machine rule. So there are many random numerical strings that represent invalid syntax and do not map to any real Turing machine. So there are, of course, a lot of gibberish and weird things that don't have a real Turing machine. Like it's nothing. It's just bullshit. Now, what information is stored on the coding tape? It holds strictly, so it goes like this, like this, like this, like this, like this, like this, like this. Now, what information is stored on the coding tape? It's strictly encoded binary rules, Gödel number of the target Turing machine that is being computed. The coding tape acts exactly like the installation of the software script. What information is on the working tape? It holds the current live contents. And so, for example, there's a working tape, there's a coding tape, and this has the Gödel number and the input word that you want to give it. This is copied to this working tape, and on the working tape, it's a live content or input word being processed by the simulated machine. The working tape acts as a user active data for being edited, and the information is stored on the state tape. It's the state, the current states that you're simulated on that moment. Acts like a CPU instructor, like tracking every single step running code. And how does you perform one computation step of stimulated Turing machine? The universal Turing machine reads the current state tape and current symbol tape 2, scans the coding tape, the first tape. So for example, this is tape 1, tape 2, tape 3. Okay, so it first read the state one, then goes up, and then goes up, scans the coding tape, then finds the exact matching block, and then updates the state, writes the new symbol, and moves the head line by line, applying the logic to the variables, and then comes back and then repeats the process. So what happens line by line every state, and then applies the rule. In the state 1, I need to do this, I need to do that. So that's what it does. What happens if no matching transaction is found? The universal Turing machine simply halts the simulation and rejects the input, or accepts if it landed on a designated accepting state. So that's pretty much obvious. Now we have true and false questions. For example, every one-way Turing machine can be simulated by an ordinary Turing machine. That's actually true, because an ordinary Turing machine is strictly more flexible. So it can stimulate a one-way Turing machine simply by never moving its head to the left or the starting block. So this was pretty much simple. Every ordinary Turing machine can be simulated by a one-way infinite Turing machine. That's also true. A one-way Turing machine can perfectly stimulate two-way Turing machine by folding the tape into two parallel tracks and making the space so that there is space here after the ending symbol. We can make this space enough and move the digits on the right hand side so we have enough space, and then because this is infinite on this side, so you make space for the negative integers on the positive of here. One-way infinite Turing machines are less computably powerful. Well, that's actually false. Both models possess the exact same theoretical computational power, because they can mechanically stimulate one another. Because you can do something that you can do on one-way tape, and you can do what you can do on one-way on the ordinary one. So it's basically the same. Then a universal Turing machine receives only a word as input. That's actually false. A universal Turing machine must receive both the encoded machine program and the input word to know what logic to execute. So a universal Turing machine receives an encoded Turing machine and an input word as input. That's actually true, because it physically requires the rules of the machine and the data to run it against. Meaning that you need an MP3 player app, the machine, and the MP3 audio file to hear music. So you need both. So this is true. You cannot just use the app player without any MP3 file. And a Gödel numbering must be injective. That's true. Every valid number must be uniquely traced back to exactly 1. It cannot say, oh, one number is tracing back to 2, so we don't know. It's ambiguous now. So two people cannot share the exact same social security number or bank number. The Gödel number must be bijective. That's actually false. Just like we said that many random numer codes are just invalid syntax and do not map to any real machine. So there are a lot of stuff out there, random stuff, which is, so y is not y is not unique. X is unique. So X is unique. X goes to if we map it, if we make a Gödel number from a Turing machine, then it must go to only 1. It's injective. But if we're looking at random numbers, they do not go back to any Turing machine. Sometimes that's possible. So it's not unique on both sides. It's only unique on the side of a Turing machine. So a Turing machine is unique for a Gödel number, but not every number that looks like a Gödel number is actually going to a machine, because this might look like a Gödel number, but that's actually nothing. So it must be decidable whether a number is a valid Gödel number. That's true. The computer must have an algorithm to quickly verify if the code is safely runnable program before executing it. So OS checks the file extension before opening a file. It's the same thing. Like, you need to know if it's even a valid Gödel number. So it needs to check first that the rules do make sense. Are they really tracing back to something? The encoding and decoding of a Turing machine must be computable. Well, that's also true, because you must be able to mechanically convert rules into numbers and translate numbers back into runnable rules, meaning that you cannot define random rules that have no meaning and they are not really working. So you need to, the encoding and decoding of a Turing machine must be computable. If you cannot even compute it, it's not computable. It makes no sense. It's random stuff. You must be able to zip something and unzip it later. So that's true, and that's also the same case for encoding and decoding something. Now, a universal Turing machine, then what's the use of it? Why did you define these rules when you have nothing to do with them? You just encoded them, but then you cannot decode them because they're random. Now, a universal Turing machine can simulate the behavior of every encoding Turing machine. That's true. By definition, a universal Turing machine is built to read and perfectly execute logic of any valid encoded Turing machine provided to it.